Hello and welcome. This is part 5 of a webinar series dedicated to the use of ATR, FTIR spectroscopy in academia. The objective of the webinar series is to give you an update on the most recent scientific publications showing how researchers in academia use REACT-AR creatively to uncover reaction mechanism, understand kinetics, and identify reaction intermediates. We started this series in early 2009. If you haven't had the chance to watch the previous webinars, you can get access to them on demand for free on our extranet, also called the AutoChem community website, if you are a registered user, or just send us an email and we'll send you the link. We will continue to have updates to the series several times a year as interesting new research is released in publication. We try to focus on the most recent papers from academia, and we also have dedicated webinars to give literature updates from the pharmaceutical and chemical industries. An interesting note is that in the last 3 months, we've seen the highest number of papers released in publication that cite the use of REACT-AR, with about 11 papers in the ACS journals alone. And it is from these 11 papers that I have chosen my case studies today, with 2 of them being very recent, only in the last month. If you're completely new to real-time mid-infrared spectroscopy and would like to have the technology demystified, this is definitely not the right webinar for you. In fact, I don't even have a single slide on the technology itself. It's focused on case studies that I selected from the recent scientific literature. We do have some excellent webinars, though, on how the technology works and how it can be applied in your lab. Again, you can watch them on demand, as mentioned earlier, on the AutoChem community extranet site, or just send us an email and request access. Another source of information is YouTube. Just type in the keyword REACT-AR and you'll find outstanding videos about REACT-AR technology. Let's get started on the papers I selected. I've selected 3 papers across a broad range of topics. I selected each one of them because there was something about the value of real-time in situ FTIR that stood out as providing key information that really helped to understand the chemistry in these publications. The first paper I selected is from the ACS Journal of Analytical Chemistry and was published on the web on June 16, 2010, so it's very recent. This paper is a result of a collaborative effort of the research group of Professor Andreas Lisi at the Institute of Biocatalysis of the Hamburg University of Technology in Hamburg, Germany, Evonik Goldschmidt in Essen, Germany, and of METTLER AutoChem, based in Columbia, Maryland, in the USA. This publication addresses solving a complex analytical problem imposed by the nature of the reaction matrix. Quantitative analysis in unstable emulsion systems is problematic, and the use of common offline methods such as GC, HPLC, or titration are highly inaccurate, or can be highly inaccurate. This is largely due to the difficulty in getting a representative sample to analyze, as there are 4 phases present: solid catalysts, 2 immiscible liquid substrates, and a gas phase. In addition, the handicap of high viscosity often factors in as well. To overcome these fundamental limitations, real-time in situ FTIR was identified as a potential method to improve accuracy in predicting absolute concentration. I attended a conference several years ago on industrial biotransformations where I first met Professor Lisi. It struck me that biocatalysis can result in very green processes, and this is a perfect example. The current industrial method for these esterifications requires solvents and high temperatures, resulting in high energy demands. Real-time analysis is a green way to provide analytical information, and not only is the information provided without having to use solvents such as acetonitrile and HPLC, but real-time information results in better processes, which can lead to less waste. The reactions studied here were the solvent-free esterification yielding myristoyl myristate and solvent-free enzymatic esterification yielding polyglycerol 3-laurate. For the esterification yielding myristyl myristate, 50 grams of liquid myristyl alcohol at 60 degrees was filled into the reactor, equipped with an in situ mid-infrared ATR probe, and then an equal molar amount of myristic acid was added to the system. When complete mixing and a constant temperature in the reactor of 60 degrees were obtained, the reaction was initiated by adding the biocatalyst, which in this case was 1% weight of Novozyme 435. For the solvent-free enzymatic esterification yielding polyglycerol 3-laurate, polyglycerol 3 and 50 grams and an equal molar amount of lauric acid were added to the column. The reaction was carried out at 75 degrees C with the enzyme Novozyme 435 in the amount of the range of 2.5 to 4%. FTIR spectra and acid value as offline data as determined by titration were correlated to reaction progress. A process curve is shown on the left, is derived by the measured offline titration data, and then is fit to the real-time infrared data. The absorption at 1720 wave numbers corresponds to the carbonyl vibration of the acid functional group, which represents the decreasing amount of myristic acid. The carbonyl vibration of the ester functional group absorbs at 1750 wave numbers, representing the increasing amount of product. It's important to point out that you can visually see a range of frequencies that change across the fingerprint region as a function of conversion, making this system ideal for chemometric analysis. For the reaction yielding myristyl myristate, a cross-validation of the quantitative model is shown on the left as figure A. A cross-validation individually removes each standard from the model data set and then predicts its concentration with the remaining data being used to generate the quantitative model. Here we see what appears to be a good correlation between the measured and predicted conversion. On the right is figure B, is the press value as a function of the number of factors, with the minimum at 3. The low number of factors here is also a good indication that there's a good relationship between the offline measured data and the response of the infrared data in the chosen region. When using IC Quant software for quantitative modeling, these plots are automatically generated whenever the model is created. The model was generated from one experiment shown on the left as figure A. On the right, as figure B, we see two additional experiments with the offline measured data closely matching the real-time data from IR. There are two things that are important to point out about this data. The first is that a good model was generated from one experiment that was able to accurately predict real-time conversion. This is not always the case, and many times the capability to accurately predict other reactions can be improved by using offline data from several reactions. The second thing to point out is how much information there is in the infrared that can be missed by offline analysis. Due to the constraints of analysis by offline methods, which are mainly the time and labor involved, you have to take a limited number of samples and live with the gaps in between the samples. Real-time FTIR provides a continuous stream of information with a new set of quantitative values refreshing every minute or so. Building on my last comment on the value of using multiple experiments to predict future reactions, this can be essential when reaction conditions change, such as when there is a variability in the raw materials, or in this case where they wanted a model that could accurately predict reactions with different molar ratios of substrates. A model was created based on 3 experiments with different substrate concentrations, molar ratios of 50-50, which are the squares, 60-40, the circles, and 40-60, the diamonds. A 4th experiment is shown on the right as figure B, which was carried out with yet a different molar ratio of 55-45 and was also successfully predicted with the previously created model. Everything that has been shown so far has demonstrated that real-time mid-infrared spectroscopy can replace offline data. This figure is different because it demonstrates that real-time information provides information that cannot be determined sometimes by offline methods such as titration. In fact, the researchers noted that to the best of their knowledge that there is no analytical method currently available that could predict at conversions below 20% due to the instability of the emulsion. On the left, as figure A shows, below 20% conversion, the errors become larger and larger the lower the conversion. On the right, as figure B shows, FTIR accurately predicts down to about 4% conversion. As there was no offline data to use as a referee below 20% conversion, the researchers used measured amounts of substrates and products and then acquired spectra to use in the quantitative model. I want to highlight just a few of the conclusions that the researchers made. That real-time in situ FTIR information in combination with multivariate data analysis gives reliable predictions for the enzymatic esterification of fatty acid esters in highly viscous solvent-free systems. That neither the solid particles nor the gas bubbles had any significant influence on the spectral data. That the online analysis of biotransformations in emulsion systems consisting of up to 4 phases is possible, making unstable 2-phase systems accessible for analytics which could not have been displayed appropriately before. And that the additional advantages of applying this technique besides the increased accuracy are as follows: no volume or catalyst loss by sampling, and the possibility of automated live analysis in these very complicated systems. The second paper I have selected is also very recent, having been first published on the web only on June 30th, 2010. It is published in the ACS Journal of Macromolecules, and it comes from the Darensbourg Research Group at the Texas A&M University's Department of Chemistry. Professor Darensbourg Group has produced a number of excellent journal articles, and I would encourage those of you with interest in his research to take a look at his publications. This paper continues on the green chemistry theme, although this was not my intention when I originally selected these papers. Biodegradable aliphatic polycarbonates are important components of non-toxic thermoplastic elastomers, which have a variety of medical applications, including sutures, body and dental implants, orthopedic fixation devices, drug delivery systems, and tissue engineering. The production of aliphatic polycarbonates has been the subject of multinational research laboratories. One process that has shown significant advances is the alternative copolymerization of CO2 and aliphatic epoxides, such as propylene oxide, in the presence of a metal-based catalyst. The reason for the interest is in part due to the economic and environmental benefits arising from the utilization of biorenewable carbon dioxide for industrial health and safety purposes. Darensbourg was inspired to further explore the activity and selectivity of the catalyst complex, shown in the above left, known as complex 1, in the presence of anions that are better leaving groups than the azide ion, that is, bromide and iodide. They surmised that this catalytic system should more effectively tune the selectivity of the Oxetane CO2 coupling process for cyclic carbonate formation and or for polycarbonate produced from the homopolymerization of preformed trimethylene carbonate, also known as TMC. The isolation of trimethylene carbonate from this process was also of interest because it could be used in melt polymerization processes with other monomers such as lactides or caprolactones for the production of important copolymers. They reported on this transformation as it pertains to the effects of a variety of cocatalysts on the selectivity of the Oxetane and CO2 coupling reaction catalyzed by complex 1, again shown in the upper left. An investigation of the nature of the catalytic species involved in the reaction was described. Additionally, the dependence of reaction temperature on the selectivity of the coupling of Oxetane and CO2 as monitored by high pressure, under high pressure, by in situ infrared spectroscopy was presented. Finally, the effects of temperature and pressure on the selective synthesis of TMC from the coupling of Oxetane and CO2 was also discussed in this paper. In a typical experiment, complex 1, with the appropriate amount of Cocatalyst and Oxetane, were dissolved in toluene and delivered via the injection port into a 300 ml stainless steel par autoclave reactor. The monomer Cocatalyst ratio was maintained at 350 to 1 to 2. The autoclave is modified with a 30 bounce or a 30 reflection SciComp, that's a silicon sensor ATR probe, to allow the use of FTIR in monitoring this reaction progress. The autoclave is pressurized with the appropriate amount of CO2 pressure, and then the FTIR is set to collect one spectrum every 3 minutes over a 24-hour period. Profiles of the absorbance at 1750, which corresponds to the polymer, and at 1770 wave numbers, which corresponds to the TMC, were recorded. The figure in the upper left shows the selected infrared spectrum of a reaction solution obtained from the reaction between Oxetane and CO2. A is the unconvoluted infrared spectra, so you see an overlap spectrum there. B is the deconvolved infrared spectrum corresponding to the polymeric TMC, or poly-TMC, and C is the deconvoluted infrared spectra corresponding to just the TMC. On the bottom right, we see the formation of polymer as a function of time with different Cocatalyst species under a pressure of 35 bar and a temperature of 110 C. It can be readily seen that the rate for copolymer formation differs slightly from each other, and the order of decreasing reaction rate was the anions in this order: bromide, iodide, chloride, azide, and cyanate. I want to add a few of my own insights here. The first is to point out how difficult this data would be to obtain, if not completely impossible by offline analysis, making in situ mid-infrared spectroscopy a perfect tool and very enabling technology. The second is that for those of you that read the paper in detail, the spectra were deconvolved to give the chemometrically pure component spectra, or chemometrically derived pure component spectra, that were needed to generate the concentration profiles without having interference from the other component. While Professor Darrenberg used a third-party software to perform this function, METTLER actually has its own algorithm incorporated into ICIR software, which we call Concert. It provides the same exact functionality. In fact, Concert, which stands for concentration in real time, will actually perform the analysis in real time, so that by the end of the reaction, the mathematically calculated spectra and their concentration profiles can be examined. The concentration profiles in the upper left represent the series of reactions performed at 110 C using complex 1 in the presence of various cocatalysts. Among the cocatalysts examined, the bromide anion displayed the highest catalytic activity towards TMC formation at the early stages of the coupling reaction, followed by the iodide, chloride, azide, and cyanate anions. On the right, figure A shows the three-dimensional plot of infrared spectra collected every 3 minutes during the copolymerization reaction of Oxetane and CO2. Figure B on the lower right shows concentration profiles from reactions obtained after deconvolution of the infrared spectra as described earlier, indicating copolymer and TMC formation with time. Reactions were carried out at 110 C in toluene at 35 bar of CO2 pressure in the presence of complex 1 and 2 equivalents of the cocatalyst species, in this case the bromide species. It is clearly observed that when using this catalytic system and conditions, the formation of TMC is enhanced at the early stages of the coupling reaction, and its concentration decreases rapidly over time. On the other hand, the concentration of the poly-TMC is initially inhibited, followed by rapidly increasing rate over the course of the reaction. They noted that the product distributions for the copolymerization reactions were determined by proton NMR spectroscopy. In all cases, good to high activity for copolymer formation was obtained, and the percentages of poly-TMC were found to be greater than or equal to 98%, with trace quantities of TMC detected after 24 hours of reaction. Consistent with the in situ infrared data, these results strongly suggest that there is an equilibrium process between the cyclic carbonate and the polycarbonate, as percentage of poly-TMC did not reach 100% even after a 24-hour reaction period. I want to draw your attention to an important point here. The combination of in situ IR and NMR data together provided the critical information about this reaction, and rarely is one analytical technique alone sufficient to provide all the information required. The key is to have the appropriate tools in the lab that will provide a more complete set of information. And many times I have seen that is the in situ infrared data that provides that extra insight which leads the researchers in the right direction. I will show these last two plots and then jump to some conclusions made by the researchers. This article makes extensive use of real-time in situ mid-infrared data and goes into a lot of detail to explain reaction mechanisms. So again, I encourage you to refer to the original publication. The upper plot shows the concentration profiles of poly-TMC as a function of different temperatures, while the lower plot shows the rate of formation of the TMC. The researchers concluded that they had shown that complex 1 along with Cocatalyst, where the anions are bromide or iodide, is an effective catalyst system for the selective coupling of Oxetane and CO2, providing the corresponding polycarbonate with minimal amounts of ether linkages at 110 C. The selectivity of the Oxetane and CO2 coupling process can be tuned by altering the nature of the anionic base cocatalysts. Anions that are good leaving groups, such as bromide and iodide, are more effective at yielding TMC by a backbiting process at the early stages of the coupling reaction. Furthermore, at lower reaction temperatures, temperatures less than 80 degrees C, the catalyst system is capable of producing polycarbonate directly from ring opening polymerization of preformed TMC via a coordination insertion pathway. I will conclude by saying that real-time in situ FTIR played a crucial role in understanding reaction mechanism and pathway by allowing the researchers to collect valuable information about reaction kinetics and the rates of formation of the TMC and poly-TMC in a pressure reactor without having to perturb the reaction and upset the reaction conditions, which happens when taking samples for offline analysis. The third and final paper that I have selected comes from the Journal of the American Chemical Society and was published on the web on February 1st, 2010, so it's also a relatively recent publication. It comes from the Brennecke Research Group at the University of Notre Dame in Indiana. The title of this article is Equimolar CO2 Absorption by Anion Functionalized Ionic Liquids. This is a JAX communication, so it's relatively short. I chose it primarily because it's an excellent illustration of how rich in information the mid-infrared spectrum is, which provides researchers with detailed structural information about the molecules. This allows them to gain a detailed understanding of reaction mechanism. I also chose it because of its relevance, again, to the greening of our world. Quoting directly from this article, the discovery of materials that selectively and efficiently absorb CO2 from flue gases is essential to realizing practical carbon capture and sequestration. Ionic liquids are promising in this regard because of their negligible vapor pressures, high thermal stability, and virtually limitless chemical tunability. Here we show how we can obtain extremely high capacity, up to 1 mole of CO2 per mole of ionic liquid, of CO2 in anion functionalized ionic liquids. The one-to-one stoichiometry of the reaction of CO2 shown in Figure 1 above has been confirmed by FTIR spectroscopy at 25 degrees C using a METTLER REACT-IR IC10 system. The FTIR spectrum of P66614 prolinate before and after The reaction with CO2 at 0.2 bar is shown below in Figure 3. There are three important features the researchers found in the spectrum. First, the prolinate NH stretch observed at 3,290 wave numbers disappears when the CO2 reacts with the ionic liquid. At the same time, the NH bending around 1,603 wave numbers, which overlaps with the carbamate asymmetric stretch, decreases with reaction with CO2. Secondly, they found no evidence for ammonium formation, which would be present for a 1:2 stoichiometry. Specifically, they would have expected ammonium bands between 3,000 and 2,800 wave numbers, and combination bands in the 2,800 to 2,000 wave number region, if ammonium ions were present. This was clearly not the case. Third, there is a new band centered at 1,689 wave numbers, which corresponds to the new carboxylic acid moiety formed from the reaction of CO2 with the amine. The researchers noted that the assignments are consistent with vibrational spectra obtained from the electronic structure calculations. This FTIR spectrum of P66614 MET, which is a methionate species, came from the supporting information and shows similar features. The NH2 group in the unreacted ionic liquid exhibits symmetric and asymmetric stretches centered at 3,360 wave numbers with a shoulder at 3,300 wave numbers. This pair transforms into a single peak with the shoulder as CO2 reacts. Simultaneously, a new broad peak appears between 1,760 and 1,660 wave numbers. Curve fitting applied to this region reveals two distinct carbonyl stretching environments. The first at 1,688 wave numbers due to the COO- asymmetric stretch of the acid of the amino acid anion, and the second at 1,718 wave numbers of the newly formed carboxylic acid due to the proton transfer from the amine nitrogen. The FTIR spectra allowed the researchers to distinguish the fractions of physically dissolved and chemically reacted CO2, since the physically dissolved CO2 appears cleanly between 2,370 and 2,310 wave numbers. The researchers noted that it was through the combination of theory, spectroscopy, calorimetry, and vapor-liquid absorption measurements that they were clearly able to show that neat prolinate and methionate ionic liquids exhibit significantly higher absorption capacities, approaching 1 mole of CO2 per mole of ionic liquid. This goes back to the point I made earlier about the importance of having the right tools available so that all the information could be collected in order to advance the research. In this case, the molecular specificity of the mid-infrared spectrum provided critical structural information, and I commend the researchers for digging really deep into the spectroscopy to find the information they needed. Giving credit to my colleague Dominique Hebreau, he presented these references in Part 4 as recent papers published by academic researchers being worth reading, so I would like to post them again. If you are interested in keeping up to date yourself on how academic researchers are using ReactIR technology, just do a keyword search on ReactIR at the websites of scientific journal publishers. The ACS website shows that about 20 or so articles have been published in the first half of 2010 that cite ReactIR. With that, I would like to conclude this presentation.